Okay, in this video I'm going to discuss linearity of expectation, and this is going to fill up the screen, so I'm not going to write down my assumptions, I'm just going to verbalize them. And this is a theorem, and it says that if x and y are discrete random variables, and c is a real number, so those are my suppositions, x and y are discrete random variables, and c is a real number, then the expectation of cx plus y is c times the expectation of x plus the expectation of y. Okay, and again, I'm not going to write this down, but we're going to need to deal with a set of possible values for each of these random variables, x and y. We're going to let s be the set of possible values for x, and t be the set of possible values for y. And there's a lemma, which is a statement that's used in a proof. And this actually has its own name. It's called the law of total probability. And it says that the probability that x is equal to a value is the sum over all the possibilities for y. Remember, t was the set of possibilities for y of the probabilities that x was that value and y was that value. Okay, probability that x is k and y is m. And that's because y has to be some value in the set t, but it can only be one value in the set t. Okay, and we're going to use that to prove linearity of the expectation, which is that statement at the very top. Okay, so I'm going to start off with the expectation of cx plus y. I'm going to write out what that is. It's the sum, I'll write what we're summing over as the last part, of ck plus m times the probability that x is k and y is m. And we're summing over all the k's and s and m's and t. All the possible values for the random variable x and all the possible values for the random variable y. Now, notice k is replacing x here, right here. And then m is replacing y. Okay, so now what we're going to do is we're going to break up the sum. I can use the distributive law on that plus sign. And to do that, I'll have the sum over all k and s. I'm going to sum over m first, sum over all m and t, of ck times that probability, plus, and I'm going to sum in the opposite order for this next term, sum over all m and t, sum over all s. Excuse me, that should be k and s. Sum over all k and s of m times the probability that x equals k and y equals m. Okay, now I can pull constants through. The c can come all the way out, since that does not depend on k. And then the k can be pulled at least out of the sum over m's, because k does not depend on m. And we're just left with the probability that x equals k and y equals m. And that's why I chose the order that I did for the summation. If the k had been summed over first, I couldn't pull this k out. But since we sum over the m first, I can pull the k out. And similarly over here, my m can be pulled through the innermost sum. So I have the sum over all m of m times the sum over all k, the probability that x is k and y is m. Okay, well, according to our law of total probability up here, notice that this is the exact statement that I have. So that's just the probability that x is k. So I have c times the sum of all k and s of k times the probability that x is k. Plus, what's going on over here? Well, this also this also can be simplified by the law of total probability. It's just that the roles of x and y have changed. Up here we were summing over all the possible values for y. In this sum we're summing over all the possible values for x. But whether you name a random variable x or y doesn't matter, and the theorem above still applies to show that this is just the probability that y is equal to m. Okay, because x has to be some k value, and it can only be one k value. So adding up all those probabilities gives you the probability that this condition holds. Alright, now we recognize over here that I have the sum of all the possible values for the random variable x times their probabilities, and we know what that is. That is the expectation of x plus the sum of all the possible values for the random variable y times the probability of those values, so that's the expectation of y. Okay. And we see that the linearity of random variables comes from the linearity of these summations, that we can pull constants through and distribute over the sums. Okay, so that is linearity for the expectation, and this will be a very important concept that will show up again and again throughout the course.